Hi, Physics 30. Today I'm going to talk about magnetic force on wires that are carrying current. So just remember that current is flowing electrons. When we talk about current in a wire, it's always electrons that are moving around. And as we know, moving charges produce a magnetic field. Now, where I'm going with this is that if you put a current carrying wire, so just a wire that has electrons moving through it, in an external magnetic field, they're going to experience a magnetic force because there will be two fields interacting. All right, we'll discuss how to predict the direction of that magnetic force. The good news is you actually already know how to do it. You use the same hand rule as for moving charges because current is moving charges. So that should make some sense. I often refer to this as the flat hand rule. We use a flat hand. Reminder, since current's electrons, you're going to be using your left hand. So, we are going to determine the direction of magnetic force on the segment of wire between the magnets that I've drawn there. Now, the segment between the magnets would be about from here to about here. Okay, in order to figure this out, we need to know which way the electrons are going through the circuit. So this is a nice reminder. They always go from the small side of the power supply, the way it's in a schematic, to the large side. So the current is going this way. All that matters for this question is that between the magnets, the current is moving up. All right, so this part of the wire will experience a magnetic force. And it's actually possible to bend wires with magnets to find out the direction of this force. We use our left hand because these are electrons negatively charged. The direction they're moving is our thumb, so they'll be pointing up. Our fingers have to point in the direction of the external magnetic field, which are north to south. Okay, so if my thumb is going up, my fingers are pointing from north to south, my palm is facing the camera. That's telling us that in this region, there will be a force out of the page. Okay, so just to be perfectly clear, I'll write it as well. The force is out of the page. I'll just run over that one more time. So our thumb is the direction of the current. It goes from the small side to the big side. So in this circuit, it's going clockwise. My fingers are the external magnetic field. Magnetic field points away from north towards south. So here we got left to right. And now my palm is facing in the direction of the force. So every single electron in this wire gets pushed a little bit toward us here. All right, so current is a huge number of electrons passing through every second. It is possible to get, a force that adds up to actually bend that wire a little bit. All right, to calculate the amount of magnetic force on a wire in an external magnetic field, you use this formula here. All right, it doesn't give you the direction of force. The hand rule does that, as we just discussed. I'll just remind us what all of these variables are. So I is the current in amps. This is the length of wire in the field that is perpendicular to the field. I don't think you'll see a question with a wire at an angle, but if it does enter at an angle, just like before, you get a sine theta term. I don't expect you're going to see that. And as I'm sure we all know, B is the magnetic field. All right, so I've just set up one little example here that we'll work through. I want to determine the magnetic force on this wire below. So I've labeled it. There are 10 centimeters of wire between the magnets. The current is half an amp. And the magnetic field will be 25 milliteslas. there's not much to talk about here. You're only going to use this formula probably 3 or 4 times in the entire course. And you just pop in the numbers here that I've given. So 10 centimeters of, well, that's L. I'll start with I. We got half an amp. That's already the units we want. L, this is going to be divided by 100. 25 milliteslas times 10 to the negative 3. All right, so we just got to multiply these together. All right, and I get 1.25 times 10 to the negative 3 newtons. Like I said, you are not going to use this formula too often. There'll be some examples in today's handout, and you may see one question on a unit test, but certainly no more than that. All right, this might be the most interesting thing you'll see today. It's when two wires are placed side by side. If they have current in them, they produce a magnetic field. Okay. What I've got is two wires with current going into the page. Just a reminder, to figure out the magnetic field, my thumb is the direction of the current, and my fingers are going in the direction of the magnetic field. I'm using my left hand, of course, because these are negative charges. So the field is going to look like this. Okay, wraps all the way around and below, kind of like this. Just adding some arrows there. Same deal for this guy, the field's in the same, sorry, the current's in the same direction. So these red lines are the magnetic field surrounding the wire as a result of the current between or through the wires. But I do want you to look at the region between these wires here. So there's two fields, and we know two magnetic fields produce a magnetic force. Let me zoom in a bit if I can. Okay, focus, looks good. What I want to highlight is the direction of the field between the wires. The right wire's field is coming out of the page and then wrapping around. Or sorry, I'll say up and wrapping around. This guy's, the right wires between the wires is going down. Okay, so if you just have this going circularly, in the region between the wires, the guy on the right's going down. In the region between the wires, the guy on the left is coming up. All right, I'm bringing this up to show you that they're negatively oriented magnetic fields, and these wires will actually attract. This can definitely end up on a test. Okay, and that might be counterintuitive. You're used to saying, well, like things repel and opposites attract. So the current is in the same direction, but between the wires, the magnetic field's opposite. That's why they attract. Okay, let me just summarize. I don't think I'll draw the other possibility. Okay, so this is all you'll really have to remember. So two wires with current in the same direction, which is what we just drew. They attract. And the opposite is true. Two wires with current in the opposite direction will repel. Okay. If you just imagine back to our drawing here, let's say we switch this right wire so that the current's coming out of the page, then all of these arrows would be facing the other direction. There'd then be like a clockwise field around the wire. that would be coming out of the page or up between the wires, and these guys would push apart. The fields would be going in the same direction beside the wires. All right, I hope this helps. Good luck out there.